Good afternoon, everyone. I'm Yuanpeng Wang from Peking University, and it's honored to introduce our work titled SymFlow, Inventory Aware Symbolic Execution for Serverless Sensitive Data Flow Detection. And it's a joint work of Peking University and the National University of Singapore. And serverless applications are naturally event-driven. A handler function may be triggered by an HTTP request and read data to a managed service. And later, another function may be triggered by that service by a queue or by a timer. And this makes the application look less like one monolithic program and more like a workflow assembled from functions and cloud services. And that workflow is convenient for developers, but it is also difficult for security tools to analyze precisely. Notice that the arrows in this picture are not normal function calls. They are event transitions mediated by the platform, so a security tool must recover context that is distributed across configuration files, handler code, and service state. And before discussing the technique, we need a precise definition. In this call, a sensitive data flow is an end-to-end value-carrying propagation from a security-sensitive source to a security-critical sink along a feasible serverless event train. And feasible is important. The train must satisfy handler logic, event constraints, resource state, and cloud service semantics. And existing research has shown that identifying sensitive data flows within serverless applications is crucial for serverless security. However, existing approaches each miss a piece of the problem. Traditional dynamic analysis has relatively low coverage, and standard symbolic execution like serverless context and CloudFlow, a SOTA static serverless sensitive data flow analyzer, is topological only and path insensitive. It cannot validate runtime mediated flows through service state. And we found that lack of connection between topology structure and runtime validation leads to over-approximate or runtime mediated flow missing. And here is a small motivating example. The first handler receives HTTP input and stores it into Dynamo database. The second handler is timer triggered, scans the database and passes the value to os.system. And there is no direct trigger edge from the first handler to the second handler. The dependency is mediated by a database item, and it is also item specific. A topology-based analysis may see that both handlers access the same table, but it cannot prove that the value written by the first handler is later consumed by the second. This example is potentially small, but it captures the same pattern we observe in real applications. Data is stored by one function and consumed later by another function whose trigger is not explicitly linked to the first one. And this slide shows the keep gap we addressed. Architectural reachability tells us what may be connected according to INC files, trigger declarations, and resource bindings. And semantic feasibility tells us whether the connection can actually execute under the constraints. Existing static tools often conflate these two levels. They may report paths that are structurally possible but semantically infeasible. And they may miss flows that are only exposed through runtime-mediated resource interactions. And in our work, we use this separation as the organizing principle. We first ask what trains are architecturally possible, and then we ask which of those trains are semantically executable. To analyze both architectural reachability and semantic feasibility together, we formulate three challenges. First, we must recover cross-function dependencies that are not explicitly declared as trigger edges, especially dependencies mediated by shared resources. And second, we must generate feasible event trains and inputs because naive enumeration produce mostly invalid executions. And third, we must validate data flows paths sensitively while modeling the cloud services that connect functions. These challenges correspond directly to the three main components of SymFlow. SymFlow has three stages. It constructs an event dependency graph, explores context-aware event trains, and then performs event-sensitive symbolic execution. The output is verified sensitive data flows that are feasible under real execution constraints. And this slide shows complete workflow of SymFlow. The left part is the EDG constructor. It takes IC files and application code as input and builds an event dependency graph that connects handlers, resources, sources, things, and dependency attributes. The middle part is the context-aware event train explorer. It extracts paths, constraints, and resource features from the EDG, and then generates event sequences and corresponding inputs that are consistent with the serverless architecture. The right part is event-sensitive symbolic execution. It uses symbolic inputs and cloud API emulation to check whether the data can actually propagate from a sensitive source to a security-critical sink. The key idea is that the EDG narrows the search space while symbolic execution validates feasibility. So the final report is a verified sensitive data flow rather than only a reachable architectural path. And then we introduce the three components. First, component 1 solves challenge 1 by building the event dependency graph, abbreviated as EDG. The input is IC plus handler source code. First, SymFlow parses declared triggers such as HTTP, timer, S3, dynamo database, and queues. Second, it scans host API calls to discover which handlers read or write shared cloud resources. And third, it annotates handlers with source sink and event attributes. Finally, it adds two kinds of labeled edges. The example on the right shows the important idea. If H1 writes dynamo database and H2 later reads it, the resource node makes that hidden dependency explicit. And component 2 solves challenge 2 by turning EDG paths into executable event trains. It starts from a source to sink backbone path in the EDG, and then adds the dependency closure. Any resource-mediated links required for the flow. Next, it enumerates valid topological orders. So if H1 must write a table before H2 reads it, H1 always appears before H2. After that, SymFlow generates or refines event inputs using EDG features, such as path constraints and resource names. The result is not an arbitrary list of handlers, but an event train witness with inputs that satisfies schemas, filters, and resource state requirements. Generated trains are still checked later by symbolic execution, so this stage gets exploration without blindly trusting the generator. And component 3 solves challenge 3 by validating the candidate train with symbolic execution. SymFlow maintains an execution context containing the current event, constraints, resource state RS, and the path condition PC. As handlers execute, the Cloud Host API emulator updates RS for reads and returns symbolic symbols for later reads. It also checks service-side filters, so infeasible events are blocked. In parallel, taint checking follows the source value through symbolic expressions and model cloud operations. A flow is reported only when tainted data reaches a critical sink, together with the event train willingness and path constraints needed to reproduce it. Conceptually, SymFlow separates architectural paths from semantic paths. A static tool may report that a path exists because components are connected in the architecture. SymFlow asks a stronger question. Can we construct an event and a resource state that make this path execute and carry the value to the sink? This distinction is the reason SymFlow can both reduce false positives and recover flows missed by topology-only analysis. For evaluation, SymFlow is compared against CloudFlow and evaluated on CloudBench plus 104 real-world Awesome Pi applications. And this table reports the main effectiveness and precision results. The highlighted overall row shows the aggregated result, 332 verified flows, compared with 243 for CloudFlow. The gain column highlights the key result. SymFlow finds 89 more verified flow overall, and we are also improving precision by 14.4 percentage points. The precision gains comes from three design choices. First, runtime dependency modeling proves invalid cross-function paths early. Second, valid input generation steers analysis toward executions that satisfy event requirements. And third, cloud API simulation checks whether data actually moves through managed service as assumed. Together, these mechanisms reduce false positives caused by topology-only reasoning and improve the quality of reported flows. And this table explains where the additional detection comes from. For declared dependency, the gap is moderate because both tools can read trigger mappings from ANSI files, and the important gap is shown in the SymFlow runtime determined dependency column. Overall, SymFlow covers 2,142 runtime determined chains, compared with 1,060 for CloudFlow. These are the trains mediated by resources, event contents, and runtime state. So this coverage advantage directly supports the effectiveness result. SymFlow also improved vulnerability discovery. On CloudBench, it finds all 32 vulnerabilities, and on Awesome Pi, it finds 14 vulnerabilities, including all 12 found by CloudFlow plus 2 previously unknown vulnerabilities that CloudFlow missed. And this result matters because a sensitive data flow is useful only if it helps reveal a practical security risk. SymFlow's additional flows shows that the improved analysis is not only a metric improvement, but it can expose security issues that were previously hidden. And then let me walk through a concrete case. Here, an attacker controls the user remark fields through HTTP input, which handler pay order stores into Dynamo database, and handler retry pay checks then reads it, constructs an S3 key from it, and stores back to Dynamo database. And finally, set order reads the key and fetch the object and passes user remark into a shell command. And there is no direct trigger edge. The handlers are connected through the Dynamo database and S3 state. The key itself is attacker controlled, and the sensitive value propagates across 3 handlers and 2 services before reaching the sink. Existing tools miss the flow because while SymFlow recovers the flow train through the EDG, constructs feasible event inputs, and proves through symbolic execution that user remark can indeed reach command execution. And there are also several directions for future work. And we can broaden the cloud service model supported, and we can reduce runtime over time by caching or incremental analysis and local model support. And third, we want to extend event train reasoning to multi-cloud and hybrid serverless deployment. Finally, we want better developer-facing explanations and repair suggestions. So confirmed flows will make SymFlow more practical for production security workflows. And finally, to conclude, SymFlow combines architectural reachability with semantic feasibility. It builds an EDG graph, explores context-aware event trains, and validates flows with event-sensitive symbolic execution. Across the benchmark, this design detects more real serverless sensitive data flows, improves precision, and expands the coverage and discover additional vulnerabilities. The main idea is that the serverless security analysis should validate feasible event train data flows, not only report reachable topology. And thank you. That's all my presentation, and welcome to the questions.
Okay, let me start. So I was wondering, can you do this work with just symbolic execution, and not doing the first part, the architectural part?
Without static analysis and event train generation, Symbolic still works, but it will work not that good because first it will suffer more exploration on the invalid sequences, and I think it's not, and it will make the state explosion worse. And so I think the main contribution is to combine the static analysis and event chain generation with the split execution. So I think.
Okay. Thank you. Other questions? Well, let me ask another one.
Okay.
So if is it possible, since you brought up the state explosion problem, with symbolic execution, is there a possibility of getting less precise results but faster?
I'm so sorry.
Can you do something with symbolic execution or your approach that can reduce precision a bit but make your algorithm faster?
Yeah. The overhead of symbolic execution is large, and it is a fixed problem of symbolic execution. And I think there are many ways to mitigate this problem. We can reduce improve the solver of the symbolic execution, or we can combine the symbolic execution with more tools such as fuzzing. And I think it's a way to make more work out of symbolic execution, and it will make the work faster. Okay.
Okay, thank you. Any final questions? Okay, then let's thank the speaker again.